Hi, it's me, Tim Dodd, the Everyday Astronaut. Welcome to Firefly Aerospace's Texas test site just outside of Austin, Texas. Now I've got something very special for you today. I'm gonna take you guys through the entire facility, check out the Reaver engine behind me, and ask a ton of questions with their CEO, Tom Rkusic. Let's get started. Hey, look at this. Hey, Tom.
Hey, nice
Tim
to meet
Dodd,
you, Tim.
nice to meet you.
Nice to meet you.
Awesome, and what are we looking at here?
This is our Reaver engine, and it's preparing for the second flight of Alpha.
Sweet, this is awesome.
So this is the new engine too.
Yeah?
We just talk to it every day, like just when you lift off. I know it's exciting, but the party's not over yet.
Hey, what's different compared to the first round, the first batch?
This is what this electrical connector here is what we had a failure in that caused the engine to shut down. So this is the power that's going to the main valves that open the engine.
Okay.
And we had the pins inside this connector fail, which just cut the power off to that main valve, and the main valve closed, and that's why we had that engine shut down on the first flight. Yeah. So
how did you determine already that the pins kind of had loosened up and everything?
Well, we found the whole set of engines.
Oh, that's true. Yeah.
So we pulled them all out. Engines 1, 3, and 4 had perfect pins. Engine 2 had most of the pins sheared inside the connector. Yeah.
Wow.
And it's very obvious from data too that we monitor the current going to the engine, and we monitor the state of the valve, and all that adds up to just simply not getting 28 volts down the line to here. Which,
isn't that crazy of all the literally hundreds of thousands of components that can come down to something as simple as that?
Yeah, I was just watching the last episode of Firefly, the TV series. You should watch that. And the last episode, the bounty hunter's there, and he's standing next to Kaylee, next to the engine, and he's like, 1,000 things, just take one of them away, and the whole thing goes down.
Yeah.
And I was like, yep. I was like, I wish I would have watched that episode a little more closely.
No, but that was an epic attempt, though. I mean, especially for a first.
Oh yeah, man! But this thing would have gone. It just wanted to go.
Yeah.
I could just feel it. You work with these machines so long, you intuitively feel that rocket was just like, for God's sakes, let me go already. You know, so much testing, so much delays, and it was just beautiful how it jumped off the pad.
Oh,
it looked very nominal, but yeah, just a simple thing like.
It is good that you got to validate even your actual launch pad, the clamps. All the umbilicals, so many things you validate on that first attempt that are probably, you can simulate them all day long, but until you actually command the rocket to let go, you just don't know how that stuff's going to go,
Yeah, it's a huge accomplishment to do that stuff. And I got, a lot of calls afterwards from people who have done this before who are like, yep, you guys are there, and you're in a different state of existence now by showing that you can do that sort of thing. Because you're right, it's just this incredible symphony of events that have to happen for all that to come off at the same time, and it was beautiful. Everything worked well. My fears about the mission really hinged on those hinges and the various mechanisms to release.
Right.
And so.
Well, even big props to GNC for when a quarter of your control authority to be able to keep going straight up after that. 15 seconds, then for the next minute and a half having 3 engines control the thing still.
Yeah, I heard the call out for engine 2 out, and it's just like take a step back from the screen, and then like 15 seconds later, I'm like, sure we're just not missing some data here, because man, it looks pretty good. You know? But then you see it starting to slow down, and it kind of all adds up. But yeah, the control part is definitely impressive, and based on that flight, I'm pretty certain we have engine out capability if it's at the right time in the trajectory. Now popping through that max Q, when things get really squirrely, no. Right. But on the other side of max Q, we should have the ability to lose an engine and complete missions, which is a good resiliency, redundancy type of thing. Yeah.
Do you think if you had it wouldn't have mattered anyway, because obviously you wouldn't have had the velocity to make it. Yeah. But do you think it would have maintained control if you had 2-axis gimbals? Because you guys are still sticking with your 1-axis gimbal.
Yeah. I don't know. It's possible. I don't know. But yeah, it's a real simplification to have a single-axis gimbal, 1 TVC actuator, and we're all about simplicity, about lowering cost, and you got to be serious about that. You don't just have nice to have things when your mantra
Yes.
is, you know, changing the paradigm.
Right.
So yeah, with single axis gimbal and 4 engines, you effectively have one big engine.
Yep.
You have those 2 axis control, and it showed that, you know,
Yeah.
with one out, that even with
Yeah.
the single axis gimbal for a large part of the trajectory, it was okay.
On the RD170, I think also is single axis on its 4 chambers, and you can basically do everything on
Yeah.
those, you know.
Yeah, you know, I spent a lot of time a few years ago climbing around under Soviet rockets and looking at things and getting inspiration from that. And really the 4 engine configuration and the single axis gimbal
Yep.
comes exactly from that.
Yep.
This turbo pump, you know, we worked with our Ukrainian partners. I had a group of about 200 people working at Ukraine at one point, and they helped us design this turbo pump. So
Yep.
this is a really unique machine. This is the first time there's ever been a real combination of Soviet heritage technology and American heritage technology. Like this thrust chamber is Space Shuttle main engine heritage with this copper nickel plated chamber, and there's a lot of know-how and heritage from Soviet rocket engines inside this turbo pump.
Really?
So this is a totally unique experiment to bring, you know, East and West together in one engine design.
Because now you're talking my language. I've been working for 2 years on an entire family tree of every Soviet rocket engine and the history, like, you know, how they're all connected. Because it all stems, you know, eventually gets back to the A4. But you know, it's been really fun to just trace even the inner lineage of, you know, turbo pumps, and this led to this, and so that kind of brings up a question for me with a fixed throttle. Does that mean you can't actually throttle down at max Q or anything? Is it full bore once it's running? It's just running, or do you have a way of throttling beyond that?
Yeah, right now it's full bore. Once it's running, it's running. But you know, we can put that variable element in there. We have it for we're planning to use on an upper stage engine.
So you don't actually throttle down at max Q like most rockets tend to, like that thrust bucket or whatever, where they, you know.
No, we just have it designed to run at about 6 Gs at shutdown. I mean, there's some subtle things we can do. We can actually adjust the tank pressure, and that'll give us a little bit of throttling if we lower the propellant tank pressure. But
well, you proved your fuselage can handle high G loads. I mean, holy cow!
Yeah.
Wow. So, what's your combustion ratio inside the main combustion chamber, or your fuel oxidizer ratio? Sorry.
Yeah, about 2.3. But the magic and what we have the patent on happens inside the head end of the engine here. We call the tap-off manifold. The way we extract that gas and the whole environment that we extract it in, and how that is coupled with the topology of the flow around the injector, all plays into how we do this. And I can tell you, this is the only tap-off engine ever where we don't have to cool the gas coming out of the chamber. Usually you have to dump like hydrogen or some diluent fuel in to get that temperature down, because it's 6,000 Fahrenheit inside there. Yeah. This turbine can only take 1,300 Fahrenheit.
Oh my gosh.
So you got to make sure that 6,000 isn't going out here, and we've designed it all so that we don't have to put a drop of fuel in it. We just, and so you're burning, you know, at that 2.30 F. That's not stoichiometric, but it's
pretty
optimal for ISP.
Yep.
So all that combustion takes place in that environment where you get, you know, good complete combustion with very little soot. Very important.
Right.
You look at
turbine.
okay, as compared to a GG, you're like running that thing at 0.30 F, and it's just puking out like a big steam engine from the 1800s. You know, black, clogging up turbine nozzles and all that. This is extracting it, you know, all that gas from the, you know, the combustion chamber where you're producing a lot less of that sort of stuff. We've never had any degradation of the turbine system. No turbine nozzle plugging, no coking. We've never blown up one of these engines, never.
Oh my gosh.
And out of thousands and thousands of seconds of development and everything, they just run. And hopefully today won't be the day.
Right.
There's some wood around here.
Right. So you don't even do a helium or nitrogen spin start or anything to?
Yeah, we do a nitrogen spin start from the ground.
Oh, right.
Although we've recently did a series of tests where we're trying to figure out how low we can go on that spin start.
Before it can bootstrap itself, kind of?
Yeah, before it'll bootstrap itself. So we've definitely been playing with the level of spin start that's required, but we do
Okay.
spin start them.
But it
Is that
doesn't.
okay?
But on the ground side, it doesn't necessarily matter, right? I mean, you can have a tank the size of a
Yeah.
semi truck on the ground side.
Yeah.
But in the air for lightning, I assume it probably matters a lot more.
Yeah, exactly, for lightning. And yeah, what we found that we can probably just tickle this thing with a little nitrogen at altitude and get it to run.
Wow.
Much lower, very low spin start requirements. Yeah, the dream would be to deadhead start it, but we haven't gotten that brave yet.
Okay. I mean, that's still amazing. I assumed it, in my head, it has to get like almost all the way up to operating speeds, and then you
Yeah.
open the valves and let it run. But I
Yeah.
didn't realize you were bootstrapping it so much. That's pretty amazing.
John, our propulsion director, is back there. He's
Hey.
I've been trying to get him to just plug the throat, and then we can like get it running and let it blow that throat plug out. That would do it without spin start.
Yeah.
Or blow it up.
So it is regeneratively cooled though,
Yeah.
too.
Yep.
So then that's kind of
Yeah,
Yeah,
that's like I said, that Space Shuttle main engine heritage, high strength alloy copper with electroplated nickel, nickel cobalt. Yeah.
okay.
Alloy
And
insert.
what do you, if it's okay, what do you use for the injector? Is it kind of a typical shower head design, or is it?
Yeah, we have two designs. We have one that we patented called Crossfire, which is a really unique, super simple injector that's in the Lightning engine. And then on this one, we use a more conventional pintle injector.
Okay. Oh, pintle.
Yeah.
Cool. Wow. And now remind me, you could actually throttle with a pintle injector, couldn't you, if you wanted to?
If you put variable elements in there to throttle it, you can. It makes it a lot more complicated
Right.
to do that. But if you get it to work, then you can also do a phase shutoff on the injector too and get rid of the main valves.
Oh, right.
So you just so that injector throttle becomes the main valve too.
Because I think isn't that what the Lunar Descent engine used, was a pintle injector to be able to handle deep throttling?
Yeah, absolutely. Yeah.
That's dang, wow.
So yeah, we'll probably get into that with our lunar engines. We'll probably look at for a Lunar Descent engine more of that variable throttling
Okay.
need. You really have that deep throttling need, or you got to use a bunch of smaller thrusters to
Yeah.
and pulsing.
Yeah, and thrust differential.
Yeah,
and stuff
to
like that,
get
and-
to kind of average out to whatever thrust you need at the time.
Wow.
But the more elegant way is to just deep throttle a pintle,
Yeah.
and so I think we'll get into that.
for
soon.
Blue Ghost.
Yeah,
Is that-
for Blue Ghost. Yeah.
Cool. And Blue Ghost, is that going to be is that going to be pressure? I assume it's going to be pressure fed, right?
Yeah, Blue Ghost is pressure fed.
Okay. Okay.
Yeah, space engines make sense for
Yeah.
that kind of mission to make
Yeah.
them pressure fed.
And use hypergolics, I assume.
Yeah,
Or,
and the other reason you do pressure fed is because you usually get into those pulsing applications,
Right.
and you're not going to be spooling a turbo pump and shutting it off in
Yeah.
100 milliseconds.
Right,
It's a little
right.
hard on the hardware.
yeah, little. Yeah, that's awesome. Man, this is so when you guys have run all 4 engines at the same time on the same test stand before,
Yeah.
correct?
Yeah, this stand has a lot of heritage. This was actually set up for the Aerospike, so you can see that there are 12 pads.
Rest in peace.
Yeah, each one of these pads was a combustion
One of the
chamber
chambers.
for the Aerospike. Yeah,
Really?
12 combustors.
So Aerospikes are my other, besides Soviet engines, Aerospikes are my other. They're the devil's engine, obviously. Tempting, but never seems to be worth it. But you guys got pretty far in development, though.
Yeah, I mean, my opinion is that they're optimal for a pressure-fed rocket. So if you remember, in Firefly Space Systems, we were developing a carbon fiber pressure-fed rocket, and let me get technical. I mean, so your specific impulse is all about thrust coefficient, and how and that comes down to how much nozzle you can put on the engine. So you can only expand the gas so far before the pressure becomes so low that the atmosphere starts to come in and
Yep.
destroy the flow pattern.
Yep. You have
So-
flow separation at the nozzle.
Yeah, so you want to make it as long as you can. Another way to get a longer nozzle is to increase the chamber pressure,
Yep.
so that you can kind of forestall that place where it crosses over to atmosphere further and further out.
Yep.
So on a pressure-fed rocket, to get that chamber pressure, you have to pay for it in the pressure of the tanks.
Which means thicker tanks.
Thicker tanks. So in the pressure-fed rocket, you're really trying to lower the pressure in the propellant tanks. But that means you're gonna have a really short nozzle
Yes.
for the reasons I just said,
Yep.
because the chamber pressure is very low.
Yep.
The way around that is the Aerospike.
Aerospike.
So the Aerospike allows you to have increased thrust coefficient by giving you a sort of a virtual nozzle extension, so that you can use short nozzles on your combustion chamber and then have that additional expansion of thrust generation on the spike.
Get the long expansion ratio that you can use at sea level is obviously the whole beauty of Aerospikes.
Yeah. But it really allows the pressure-fed rocket to get the thrust coefficient it needs to be viable at the end of the day. I don't think the pressure-fed rocket for orbital launch is viable without an Aerospike. Really? Now, when you get some Ukrainian friends and you get turbo machinery and you can just go up on pressure, it's less attractive. It's not as necessary. It's easier to go with a more conventional type nozzle.
Okay, yeah. What was the final death for you with the Aerospike? What was the final thing that closed, or you just go? You know, was it the fact that you kind of got your hands on turbo machinery and people that were willing to design turbo pumps? Yeah,
it was really just, we would have kept on going and flown Aerospike with Firefly Space Systems if we hadn't run out of money and shut down and all that. So when we got the new investor, Max Polyakov, he's Ukrainian. He has heritage in the family of Soviet rocket science, and so a lot of connections. So Max was able to connect me in with technical people in Ukraine that could help us with the turbo machinery, which put us years ahead. I mean, that's just, it's a really hard thing to do. So then if you immediately connect with people with that expertise, it's just like a quantum step.
Right.
So we were immediately able to connect our combustion chamber design, the Ukrainian turbo machinery design, and then I decided to take that little bit of extra risk for the big reward and to go for it on the tap-off cycle. So that was completely just a Firefly call. So to connect these two, we decided to go with the most elegant solution, which was tap-off, and unfortunately it worked. I can tell you the first time we were up in that control room and we ran it, and you shut the spin start off and the rocket keeps running, it's pretty wild.
I can imagine.
It's working, this whole principle of operations working, and that was a really exciting day. One of my most exciting days here, I'd say, is just very gratifying to see the science work, the risk to pay off, and to like, we just did something no one in the world has ever done. With LOX-RP propellants run a tap-off cycle rocket engine that's designed for orbital spaceflight. So make history out here out in the field is pretty amazing day.
Yeah, absolutely. Yeah. So tell me, is there actually any heritage?
Hold on, let's say, do you guys need to work on something? We can step back a little bit.
True. Well, you guys trying to get ready to actually fire this thing up, and we don't want to be here when that happens. We'll give them room to do that. Is there anything that as far as the turbo pump and Ukrainian heritage, is there any actual heritage from other Soviet era engines at all that you know of, as far as like is like that turbo pump similar to I don't know, something like an RD-264 or something like that? Or that pump is 100% clean sheet designed. Okay. But the Ukrainian team, they're very process oriented, and they just have a lot of design rules and methods that they use, and just basic construction methods that are different than what we do. For example, the oxygen pump and the fuel pump in this engine are separate. They're coupled. They have a shaft coupler that couples the two, but you can actually remove them individually, because over there they like to test them individually, do flow tests with them, and then assemble them into one device. So that's something that I hadn't seen before. So it's a single shaft, but it has a linkage that you can like break it apart and. Yeah, it's a shaft with a collar that couples the two shafts together. Cool. And when we look at it, it's like, wow, man, that's going to have to be really tight tolerance to make sure that power gets transferred right, and it doesn't. But these are things that they learned over the years how to do, and we were benefited from that. You guys aren't putting dents in the nozzle now.
Sorry about that. Just a little nervous.
Now the pressure's on.
Yeah, we're all nervous these days. That one's going to fly. This flight too. This thing's got to work.
I haven't done that in a year.
Don't worry, the whole world will see it now. No big deal. We will cut that out. Don't worry.
Oh, that's awesome though. But so with the and obviously the Soviets have the Soviets had a lot of experience with having really high temperatures at their turbine too. I assume was a pretty big limiting factor. Obviously, you had to figure out how to cool it enough to have the turbine survive. But was there some heritage there that you're like, hey, this turbine that they designed can handle higher than what other companies are maybe operating at.
Yeah, I'm not so sure they have higher turbine temperatures than we do. They generally do full stage combustion engines, so they have hot oxygen.
Yes.
I'm not sure the absolute
rich.
temperature is higher. It's just
Oh,
the fact that it's very reactive hot gas as
Gotcha.
opposed to inert hot gas. I mean, the temperature is really limited by the rotor dynamics and the materials, and the materials are Inconel, and the rotor dynamics are just a disc rotating.
Right.
So I don't think there's anything
Okay.
necessarily different. The turbine wheel in this engine looks very similar to turbine wheels I've seen
So it's
in
more
other
about
American rocket engines.
the metallurgy and the fact that it has to handle the oxygen-rich environment as
Yes.
opposed to the actual end
Yeah.
temperature.
Yeah, that's where, if you want to go to the next level of complexity, when you start getting into oxygen-rich stage combustion, liquid oxygen's super friendly. It's hard to get it to do anything bad. I've even had, not here, but at other places, I've had multiple engines where the liquid oxygen caught aluminum pieces of the engine on fire, and the liquid oxygen just cools it and quenches it and puts it out. It's like, oh, sorry
Really?
about that. Didn't mean to cut your engine on fire. I put it out. It's no big deal. When you get into hot oxygen, gaseous oxygen,
Yeah.
white flash of light, engine's gone. It's just like gone. This is like consumes it. They're like, what the hell just happened? It's a
Wow.
completely different problem, which required many years and extreme amounts of money to solve the problem of coating the materials in the environment to be able to deal with that ox-rich environment. Now here in America, in the last decade or so, we've come up with metallurgy that doesn't require these advanced coatings. So we, in principle, can build ox-rich stage combustions here that are even more robust than what was done over on the Soviet side.
In the 50s already is when they started doing ox-rich. Stage combustion. It's just
Yeah, they just
crazy.
go for it. Get the maximum thermodynamic efficiency you can. So
It's always funny to me that while they were focusing on stage combustion, the United States, and almost never touching hydrogen, the United States was doing hydrogen and then solid rockets, and that's something that the Soviets almost never ever did, was anything solid. It was all like stage combustion and lots of hypergolics,
yeah, major hypergolics.
Yep.
Yeah, they had the SS-18 Satan missiles, which really caused us big problems, and was part of a lot of the negotiations during the Reagan era. Yeah, those vehicles could sit underground for 20 years. That's what they're designed to.
Yeah.
Put it in the ground 20 years, don't touch it, liquid fuel rocket system.
Yeah. That's crazy.
That thing under the tarp is really the world's largest brazing oven for rocket engines. There are two of them in the world. One is there, and the other one is building the RD-180s in Russia. This was used by Aerojet Rocketdyne, but we acquired it last year and are setting it up our own facility. So we'll be able to advance our engine fabrication tech and move away from nickel-plated chambers to brazed steel wall chambers.
Oh wow. Okay. That's cool. So the Reaver and Lightning will already be evolving beyond what we see today.
Oh, definitely. Yeah, let's go up here. We can maybe get a bird's eye view. So this is our machine shop, and one thing we're doing at Firefly that I don't know how unique it is, but we're really segregating the company into self-sufficient business units in order to just make sure everybody has the resources they need to do what they need to do. We're taking on a lot of projects. We're doing lunar landers, alpha rockets, beta rockets, space utility vehicles. So part of doing that is we have to have the discipline to make sure all these projects have the resources they need. So this machine shop, for example, is not just going to be like a, hey, come in and get your stuff machined. This is being set up as a commercial aerospace machine shop, and they're going to work like that, and we'll even do external jobs for other companies. So up here is kind of like where all the office and programmers and such are going to be. But if you go along here, you can look down and see them working on rocket engine parts. See, obviously somebody was working on a combustion chamber.
Wow.
A lot of copper.
All that copper.
It's probably one down on one of these machines we can look at. There's one over by that bin
Yep,
You can see that was recently machined.
chamber over there.
Yeah.
That's awesome.
These DMG machines are really advanced 5-axis machines with multi-pallet tool chambers. Like you can see that machine that's closest to us on the right has 3 pallets. So you put 3 pieces of material there, and then give the machine the program, and it knocks out 3 parts without, lights out without humans.
Without interruption.
Yeah, just out interruption. Just boom, boom, boom. And right here you can see some Reaver tap-off manifolds being machined.
Oh yeah.
Those are Inconel parts.
Wow.
Now we're really getting into 3D printing those in the future, but for the time being we're doing some just by working with Inconel forgings, which hogging out Inconel forgings is that's kind of, it's tough. In Inconel, the harder you push on it, the harder it pushes back. It work harder than as you're machining it. So
it's the donkeys of metal.
Exactly, that's a good way of putting it. Yeah, harder. No. But we're adding a lot of machines here. We just hired a new machine shop manager that has experience in mass production of combustion chambers. So we're going to be following his guidance to buy some really kick-ass new machine tools that allow us to machine these thrust chambers in a matter of hours instead of days like it takes now.
Wow.
But over on the right, we'll walk down on the floor, but on the right you can see how the thrust chambers start. They start as a forging, just kind of a rough shape, that copper thing on the floor.
Yeah.
It's kind of a rough shape. And then we'll go down and you'll see how that gets turned down. So I think we start with about 1,200 pounds of material.
Wow.
And then by the time it's done, it's about 80 pounds, I think.
Oh my
So, yeah, that's one thing we want to, we look really closely at additive, and when you think about those how much material you're removing, looking closely at additive, but on these sizes, and guaranteeing that you have the material properties you need in a printing process, we just haven't found that combination yet, and we haven't found it being economical, even though potentially in an additive process you could use less material. At the end of the day, if the part costs more,
right,
it's like, why?
Yeah.
Yeah, so really I think 3D printing for some smaller parts has been proven really beneficial.
And probably in the
from us.
prototyping phase is
prototyping,
fantastic.
You got it, exactly. If you want to make something fast and try a bunch of different permutations and iterations, it's the way to go. But for large scale things like thrust chambers yet, I just haven't seen it.
Yeah. Wow, you guys have a lot of space. You're looking to be expanding like crazy, aren't you?
Yeah, like I said, I'm really serious about this machine shop becoming a commercial shop, so I'm giving them all the space and offices and stuff they need. You'll have people doing pricing, you'll have people ordering materials, you'll have people managing tooling, and then the programming of all the machines. It takes quite a few people.
Did you guys see a pretty big surge after your first flight attempt of people, new hires, and just a lot more excitement around the company?
There's definitely energizing the company. I mean, my whole mantra, the corporate culture I want, is accomplishing great things and having fun along the way. So every time you accomplish something bigger and bigger, it just kind of motivates you more and empowers people more. So I think we're definitely got a little more swagger. Yeah. We're still humble because the rocket's always humbling you, but yeah, definitely people we're hungry, we're pissed off, and we want to get back to the launch pad. At least I am.
But again, you validated so many things for a first launch attempt that it has to feel, at least you're on the right direction, and you got it coming next.
The rocket, I've always, as I said before the launch, I have complete confidence. The rocket's designed well, and there's nothing in that first launch that tells us we have to change anything, except move some connectors around, things like that.
Yep. That's great. Yeah. What is your timeline for the next launch?
We'll be ready in December. we've got regulatory stuff. We got to get through our investigation, get final buy-off from the FAA. We might do a slightly different trajectory. So there's some updates. But
yeah, I was surprised. I didn't realize until literally like the day before launch that you guys were flying so retrograde.
yeah,
What was that? What was the purpose of that as opposed to a little more polar?
scary new rocket.
Get it away from land. That's crazy. I didn't realize that.
Yeah.
That makes sense. I mean, you're just trying to get to orbit. You're not trying to.
Yeah, we're trying to do, it was a test flight.
Yeah.
But yeah, I mean, when the thing's going next time, it'll be over Hawaii in like 15 minutes after launch, which is pretty wild.
Wow. Yeah. That is.
Let's
That's
see if we
crazy.
got any. No, I don't think we have any. No thrust chambers up today.
No, not today.
Yeah.
There's that one that's over there that I did. But
Here's one of these turbine wheels if you want to look at it.
Yeah.
Yeah, you can take a picture of that. It's okay. It's just pretty standard.
Wow.
So that's rotating about 33,000 RPM inside the engine.
And that obviously has to be extremely precise and extremely well balanced.
Extremely well balanced. But what's amazing is that, 900 horsepower you get out of that turbine wheel to drive the pumps. So just the pump to pump the propellant's 900
Yeah.
horsepower. It's pretty cool.
And I love that the little buckets, the little buckets that catch gas. It's pretty crazy that that they can handle those kind of forces and that kind of pressure and temperature and everything.
Yeah, I mean, you're converting the kinetic energy of that gas into the kinetic energy of this guy.
Yep.
Like you said, it's a
there's it.
bucket. It just catches it and
Yep.
turns it. This guy goes faster, the gas goes slower. So
That's awesome.
So
That's very cool.
this is Brett. He's one of our.
You were great, man. I really
Hey, thank
enjoyed
you.
that. Yeah, thanks a lot.
Well, I really enjoyed your launch. That was amazing. We really, I was just so excited about it, honestly. It
Can't
was-
wait for the next one.
yeah, you guys are gonna knock it out of the park in the next one. I know it.
Yep.
I know it. Is there some kind of a DeLaval nozzle that exchanges the pressure into higher velocity at the turbine, like before the turbine?
Exchanges the pressure and
tap.
higher velocity. Yeah, definitely. Yeah.
Tap
So
off.
the tap off gas comes in to a DeLaval nozzle. It's pretty interesting geometry. I don't know if we have one around here, but it's a scarfed nozzle. If you've seen, if you take a normal nozzle and you just cut part of it off,
Yeah.
that's called a scarfed nozzle. So it's kind of like half of a nozzle.
Really?
Yeah, it expands in there, and so there you take the pressure from the tap off, which is about 1100 psi. You expand it through a nozzle to about 30 psi.
1100 psi is coming off that tap off?
Yeah, it's coming right out of the combustion chamber. Combustion chamber runs up to 1300 psi.
Really?
So there's a-
Sorry, what's that in bar? That's almost like 80, 90?
It's about 90 bar. Yeah.
Wow. Okay, that's higher than I thought, considering it's, I always assumed that you had to have,
No, we can do anything with the tap off that you can do with the gas generator, and probably more efficiently. Yeah. So
You're moving a lot of parts.
We're moving up. I mean, 1300 psi for kind of first generation engines, pretty sporty, pretty
Yeah.
good. It's a lot higher than engine programs I worked on for other companies.
Yeah.
For first
Do you actually
shot.
think you can get beyond that? And
Oh yeah.
Yeah?
I mean, the technology, like I said, that space shuttle main engine technology, that could go to 3000 psi chamber pressure. Now, it's not smart to do that with an open cycle engine, but has to do with the turbine efficiency, pressure ratio across the turbine. That 1200, 1300 is about optimal. Also, with LOX-RP propellants, some of the products that condense on the surface of the chamber are beneficial for inhibiting heat transfer to the wall.
right.
So once you get up above about 1200 psi, that sort of soot carbon layer starts to come off. So he kind of runs away. Your cooling problems get worse very kind of precipitously as you go over that mark. It's not just 100 psi is a little bit different because your soot goes away and now you've got much more heat transfer to the wall. So there are other factors that play into what's going on in there.
So the coking on the combustion chamber can almost aid as as an insulating barrier?
Oh, it absolutely does. It's a
Really?
big, it's really effective thermal barrier coating for free.
Really?
So all that soot you saw in my face and in that chamber, that's great for thermal barrier coating.
I did
It
not
inhibits the
rea-
heat transfer.
Never thought about that.
But if you go to too high OF or you go to too high pressure, that goes away and it's just pure copper, like, you know, exposed.
Yeah, that's crazy.
Yeah.
Wow.
Which is a unique part of the LOX-RP engine, and LOX-RP is amazing for a boost propellant. Frankly, I don't know why anyone would use anything other than LOX-RP for boost propellant. Certainly for upper stages, higher energy propellants are better. But when you look at the impulse density, as you call it, or you know how much impulse you get per unit volume, it's on par with anything out there.
Yeah.
You know, methane, better performance, but bigger tanks, and it all kind of washes out to be equal. But then you got all the hassles of lower explosion limits and handling that
Cryo.
stuff and cryo, yeah. So I mean, it's pretty bizarre when you think about Rockefeller and those guys were like making kerosene back in the 1890s, and it's the absolute perfect thing to go to space after all these years.
That's crazy.
Yeah.
That's awesome. Huh. So, and with, do you guys do any additional like film cooling at all? Like on the injectors or anything to, because that's another way of cooling the combustion chamber too, is an additional layer of fuel or something, right? That.
Yeah, we found that we can run the barrels, you know, without any film cooling at all, which is another thing that cranks up efficiency. On some engines, early on we put film cooling in the throat area, because that's where you get scariest. That's the highest heat flux is there. But we've had engines we've run without film cooling. Eventually, no film cooling, but the early ones, you know, were more conservative, have film cooling in them. Also, like that first flight of Alpha, the engines ran at 2.2 OF, you know, which is just a more conservative, cooler running combustion temperatures. But then we'll just incrementally march up. You know, we've run these engines at 2.4, 2.5 OF and haven't had anything crazy happen yet.
How do you cool it, just the throat? Where do you have to inject a separate place to inject fuel or something at a throat? I never understood that.
Yeah, so wish we had a chamber here with cooling channels in it. So that chamber will have cooling channels milled into it.
Yep.
And then we'll put wax in those channels, and then we'll electroplate nickel over that, and then we'll melt the wax out, and now you've got channels. That's how we make our cooling channels.
Okay.
Now, before you put the wax on, when you have those channels, if you just go a little bit above the throat and use an EDM, about 12 mil EDM tool, electro discharge machining wire, and just pop little holes through those cooling channels into the chamber before you plate it. Now you plate it, and in those channels you have little tiny holes, an array of little tiny holes above the converging section, and that will inject jets of cold fuel.
So basically, like intentionally will leak a little bit of cold
Intentionally
fuel.
leaks, exactly.
Interesting.
Yeah, and I've even seen these engines are amazing. And I haven't seen this here as much, but I've seen places where the engine will actually erode itself down to the point where it starts leaking, and then it's happy, and it doesn't go any further. It just like self-regulates.
Yeah, interesting.
Yeah.
Almost like an ablative nozzle unintentionally, but
Yeah,
self-correcting.
it reaches an equilibrium, and it doesn't blow up, it doesn't go away, it just kind of erodes back so that the wall's thin enough to get the heat transfer, and sometimes it leaks too, and off you go.
Crazy.
Yeah. So,
Wow. That's awesome.
yeah, the space shuttle guys did us good getting the stuff working.
Yeah, 100%. Yeah.
Okay, Mile covered with soot.
No, you're good.
I've been touching my face again.
Working man.
Yeah.
Awesome.
Yeah.
145.
Aside, maybe this wasn't supposed to be a propulsion interview, but say I like to get involved in that stuff.
Well, I love all the little nitty gritty details like this. Especially when I get to talk to someone that knows what they're talking about. I'm going to pick your brain all day. This is fun stuff for me, and my audience in particular, I think, tends to really like, getting into these things that they don't get to hear about all the time.
Yeah.
And unique solutions. I love that every different company, every different engineer will have, tackle the same problem with a different solution. And it's just cool to see you guys using the tap off like that. I think that's awesome.
Yeah. Yeah, so this whole place is kind of like living in a home that you're building around you while you're living in it, for people that have done that. So, yeah, a lot of these buildings are catch-all. We're moving a lot of things to Cedar Park. You'll get to see the spacecraft facility, and we're going to move the final integration of the rockets down there soon as well.
Cool.
And we're building a huge, like world-class composites facility with robotic auto fiber placement machines. If you see there's dirt moving over there, that's going to be a big facility, twice as tall as these buildings, twice as big. And so we have this amazing aircraft technology, auto fiber placement machines that we've procured and we're going to use to build rockets.
That's awesome.
Because as you saw, all this stuff is hand built up by hand.
Wow. This is bigger than I thought, to be honest. Just being up close and...
Yeah, this is just the LOX tank. This is just the liquid oxygen tank for first stage.
And again, and you have no liners or anything, it's just straight on?
Yeah, nope, yeah, no, straight up. Yeah, the technology of how we figured out how to put domes and stuff in here was really hard, but it's one of our innovations.
Yeah, that's my understanding. It's pretty darn hard to keep LOX happy in a pure LOX like that happy in a carbon fiber environment can be pretty difficult.
Yeah. But it's like I said, LOX is pretty well behaved from a reactivity perspective. We have never had any problems with any of this stuff catching on fire. So here's flight 2 going together. I think that was flight 3 that we passed. So this is flight 2, getting ready to integrate engines. That engine that's out there testing will be integrated on here. But you can see the whole first stage assembly, fuel, inner tank, oxygen.
That's amazing.
So the team's trying to convince me to paint something fancy on the bottom here. We had the Phoenix on the first one to kind of represent, you know, just the resilience of the company, you know, having setbacks, bouncing back, coming back to life.
Rising from the ashes.
Rising from the ashes, all that. And so I wanted to keep the second flight pretty simple, A-help, you can see. But now they're talking about putting some like highly decorative Phoenix on it or something. So we'll see what they come out with. So Composites is working on like flight 5, I think. All these tanks over here.
Jeez.
So
yeah, you guys are cranking these things
they're
out.
they're serious about making that flight right next year. So by the end of next year, we'll want to have flown 5 more rockets. Wow. So we're confident in the design, so we're building it. And going ahead.
Yeah.
This is probably the flight 2 fairing.
And you guys did something a little different for your...
Yeah, you can see I'm making the COPVs over here. Sorry.
Yeah, you're good. Yeah. For your first flight, you went ahead and kind of certified and did a lot more steps that'd be unusual for a first flight. If I recall, you were certified and ready for flight by doing all the cataloging and everything that you'd normally do for a customer. Is that correct? I feel like there's maybe some extra steps you guys did even on your first flight that'd be...
Yeah, the scrutiny that you undergo at a range like the 30th is totally different, for example, than a NASA range, where you're basically following industry standards and OSHA and things like that. At the 30th and the 45th, at the Air Force ranges, you're following that whole regimen that ULA and all the heritage companies have to follow. And you know, we purposely did that. You know, we didn't want to just like go to Alaska and just start blowing up stuff. You know, I really feel like the rigor that went into getting everything right for the range translates into quality assurance, really, that's just going to make the product mature faster than just running out there with, you know, stuff duct taped together and trying to see what it does.
Yeah.
So that's interesting. Are we doing a cube? That's our new cubicle COPV. I may have to, that might be an intern project. I may have to have a conversation with them about pressure vessels. I don't know what that is.
That's cool. That's funny. That's funny. Someone just trying to strengthen the shoebox for fun.
Yeah. So we're building up all of our assembly areas. We're getting new buildings and stuff. There's just so much stuff crammed in here. These guys are building valves. They're building composites over here, building engines over, plumbing over here. So they have template engines. So they're building all the fluid lines. So these are just like like when you're making dresses, like pattern, you know,
Right, pattern
pattern
fitting or
dummies.
whatever. Yeah.
So they can come up here and
Double check all the fittings
and
and
double,
everything.
yeah, double check and weld stuff up.
That's
We
awesome.
can walk through here. Yeah, we may edit some of your video here on some of these tools are kind of proprietary.
Gotcha.
But, so building the composites, you need to do it in this clean and cool environment. But it's really arts and crafts at this point. You have these tools, fairing tools, dome tools, barrel tools, and it's folks in here laying up patterns one at a time. We have a laser projection system that we use for a lot of these operations where it'll project the pattern onto, and all they have to do is lay it up, lay it up, lay it up. Just follow it
pattern.
and say go, and it puts the next laser thing up. This fairing is one that we don't have programmed in there, but some of the other parts we do.
So it's almost like a paint your own, paint by code, but it's fairing or like carbon layup by number.
Yeah, it'll actually put the number, laser project like that.
No way.
Up there and with the exact shape, and you just stick it right where it'll have the outline up there. You just stick it right there.
That's crazy.
Wipe it down, peel it off, and then just say go, and it just moves around.
That's insane.
Yeah, but when we get the auto fiber placement machine, it'll just go in here robotically and lay all this stuff up. It can move like 15 miles per hour. This head of it's called a toe. It's a unidirectional toe. So this stuff is all fabric. It's like woven fabric. If you look at it, you can't really see it there, but it's like woven fabric. The stuff that goes in the auto fiber placement machine is unidirectional. So the benefit of that is it can align the fibers exactly in the direction of the force.
The loads, yeah.
Instead of with the fabric, the 90-degree one goes along for the ride, right? Because it's fabric.
Right.
So often you do them 45 to where the load is. But with the uni, you can just line it right with the load and get an even more efficient structure than you can with the fabric.
Wow.
So it's fast, lower cost, weight savings, optimal supply chains established. They build 777s with this technology. Just write a $10 million check and you get one.
Sweet. Where do I sign up? That's awesome.
And then so for the fabric, it just comes in rolls like this, rolls out here, and this table cuts those, a CNC cuts those patterns.
Wow, that is cool. That'd be fun to be the person that has to design all the shapes and know, especially with the fairing where it's a little more contoured, you have a little more, unique shapes and stuff. It'd be fun to have to figure out, how to do that as efficiently as possible.
Well, we have a partnership with Siemens, and they make NX and Team Center, and they have some other carbon fiber dedicated tools that do exactly that. And the cool thing is it helps you lay it all out when you're designing it, and then it takes all that layout and takes it to the environment where you can do the stress calculations directly, and then it can export these patterns for you, and then it can program that laser like all in one. So you just do one model, and from there on it just does all this other stuff automatically.
Wow.
This automation. We're just getting into that. That's going to be a really cool upgrade next year.
That's awesome.
So there's some other tricky things that you have to do, like so our tool is not long enough to do the entire liquid oxygen tank. So we have to actually splice multiple sections together. And they're multi-millions of pounds of force when this thing's pressurized that are trying to rip this like millions of pounds, okay? So, and there's liquid oxygen inside of here, so nothing can crack. So getting this joint to work was a technical challenge for us, and they figured it out. But we've ordered a tool that's long enough to do the whole thing now, so it'll eliminate that step. But
that's cool.
That was a big technical achievement. And then getting the, how do you seal these tanks out? We found a way to do it completely with carbon fiber. So there's no metallic, you'll see there's no metallic joints here whatsoever, which is important in the cryogenic for the cryogenics, because one of your big problems is differential thermal expansion.
Right.
Everything gets cold. The stainless steel or whatever is like, I'm cold, and the carbon's like, I don't feel anything, you know, and they end up separating.
Expand at different rates, basically.
And then,
right?
so then you get cracks and leaks and all that stuff. So we spent a lot of time figuring out how to do almost everything in just carbon without any of those metallic interfaces. So yeah, we're in the process of building that up. We're gonna get rid of all these trailers. These are my little beautification projects. I'm building parks. I'm gonna build another park here when I get rid of this trailer.
Awesome.
Looks like we need to build some parking lots.
Eventually.
So in these trailers, these tents, I have some goodies. Did you see these rocket parts last time you were here?
I saw the, it was almost like an H1 or something. It was some weird variant of not the H2, but it was some other weird engine.
Yeah, so that's that engine there. So this engine was the TR, I think we should go look at it. Hold on.
If I remember right, it was like TRW's attempt at the J2, maybe?
Yeah, you got it. You know exactly what's going on here. Yeah, I just want to make sure I think it was Aerojet's attempt at the J2, and Rocketdyne won with the J2. Yeah, I think it says Aerojet on here somewhere.
It's such a unique engine.
Got some wasps living in here. This is interesting there. If you can get a picture of that wasp going in there.
Yeah.
That's actually, those wasps have caused many a problem with rocket engines. They're called mud daubers. And what they do is any little hole, they just find a little hole and they go out, catch some grasshoppers, chop them up, shove them in the hole, get more grasshoppers, shove them in there, go in there, lay some eggs for the babies, and then they seal it with a mud seal and fly off, and then the babies are born. They have a good snack. But many rocket engines, and I had this problem when I was running the SpaceX's McGregor site a lot, and I kind of learned my lesson there. We had many of these valves work on the principle of like pressurizing something and then venting it, and if it doesn't vent, then then like a main valve will stay open. So we've had like these mud daubers, unbeknownst to us, will clog like a vent port, and then you go to run the engine and go shut it off, and it just keeps going. And an engine blows up or something, and it's because of it.
No.
Wasp.
How do you avoid that? Do you just purge everything?
They have these wonderful little screens that you screw on the fittings, and they just have a screen on them so that the mud dauber can climb in. Yeah.
Gotcha.
Yeah, so anyway, yeah, I think this was Aerojet's version of the J2 that just never quite made it. So it's a LOX hydrogen Apollo experimental engine. So we're going to clean it up and give it a proper display at some point. It's just in here temporarily.
And it looks like it's dual shafted.
Yep.
That's cool. Wow.
Yeah.
Huh. That's crazy.
So
it's got to be pretty rare. I feel like there couldn't have been too many of those things made.
No, I think it's got to be pretty unique. It's probably worth a lot of money. It deserves a better home than out here in a tent.
Hey, I'll take it. I'll put it on display.
Yeah. Yeah, I think the neat thing about working with Elon and Jeff is they're both really understood the technology, and I always thought it's an important part of these types of companies that, at least when you're starting up, that the leadership can discern, good ideas from bad ideas. Careful with the sharp edges.
Yeah, and to be able to lead from a position of knowing the technology as opposed to just kind of always just from the business end of things is probably very beneficial when it comes to a rocket company.
Yeah, and I think if you just look at the various companies that are out there, it shows in the results. Peter Beck is really into the technology, and they've made a lot of progress quickly.
Yep. Are you, now if I recall, so Alpha has no plans on ever being recoverable or anything, right? But that's what Beta's for? Is that my understanding?
No immediate plans. I wouldn't rule it out, but really we're focused on Beta and the reusable parts. Because Beta needs to be, really cost competitive on a dollar per kilogram basis. Mm-hmm. Alpha less so, because it gives you dedicated mission capability where people are willing to pay more for cost per kilogram. But Beta, it'll be able to do GTO missions, and it needs to be low single digits, $1,000 per kilogram. So
That's awesome.
reusability is going to be important.
And that's your test stand out there, the two of them, right? That's
Got stage test stand, then structural test stand over on the far left.
okay.
Behind this telephone pole is the quick
That's
disconnect stand. So that's where
Okay.
we practice that. We actually simulate the rocket moving up and pull the
cool.
QD off so that we get all the dynamics right. And then the little walls you see behind those 4 tanks, that's a component area where we can take things to burst and such.
Cool.
But next up is to build some beta size stuff.
Yeah.
And there's some betas. You guys are going to be so excited. There's so much going on with beta. Crazy stuff going on with beta.
So tell me.
I can't tell you anything.
Can't tell me anything. Not even. Excuse us. Not even. Not even if it's gonna have the same engines or anything.
I think. So anyway, this is where we build a lot of the test stands and such. Well, welding. I don't see anything major going on right now. But the interesting things about beta are going to be, first of all, it's going to fly first, just like Alpha flew first. So, relativity and Rocket Lab, catch me if you can. And one of the things we'll do, it's not just about technology, it's about business relationships. So I think you'll see some interesting relationships we have with various entities to bring the beta development along quicker.
That's awesome.
So here they're getting ready to run an engine test. So we have 3 control rooms here. This one we use for the stage testing. This one for engine testing. And then there's one on the other side that's for structural testings. Wow. So pretty lightweight operation. You see it's basically really 2 people that can run the whole test. There's one responsible engineer who's sitting there. So you have a test engineer, a test conductor, and then a test director. So the test engineer the test conductor is reading off of a procedure that's established, that's been run 100 times. And the test engineer's executing the commands to prepare the stand and execute various auto sequences. And is also just watching and monitoring the general health of the stand. The test director is representative from the propulsion department, and he or she is carefully monitoring the health of the rocket engine and making sure it's ready to go, or calling it abort if there's an issue in some point. And then if we do have aborts, the test director looks through the data, adjusts aborts and things like that to get ready for the next run. So that's basically how it works. But you can see, looks like they're got everything cleared out since we were out there, ready to go. So this engine's, this one must have run because it had sit on it, didn't it?
Yep.
So I thought this one was brand new, but so that's conditioning the stand, letting liquid oxygen go through all the lines leading up to the engine to make sure everything's cool, take it from the 100-degree Texas sun to, we like to run the liquid oxygen about minus 295 degrees Fahrenheit. So it takes a little bit to get all that stuff cooled down. So
Yep. To thermally not shock it.
Yeah, I mean, you don't want to put like minus 290 or minus 285. That's hot by rocket engine standards. And if it gets hot, then it's like it cavitates. So when those turbo pumps are trying to run at 30,000 RPM, you start getting bubbles because the vapor pressure of the liquid oxygen is high because it's warm. So that's really the main reason we have to get everything nice and cold.
Wow. That's crazy.
Now, SpaceX, they take it a step further and they try to cram more oxygen into the rocket, so they supercool it. So whereas we go to minus 295, I think they're probably running at minus 320 or something like that.
Yeah, it's 207, minus 207 centigrade, but I don't know what that is in Fahrenheit.
Yeah. All right. Well, you got your European
Yeah.
unit stuff.
Yeah.
Well, if you're a rocket scientist, you'd say Rankine, but maybe I would understand. I don't understand Celsius. Kelvin and Rankine, absolute temperatures.
Yep. Yep. So how far are we away from you guys lighting that fire?
I don't know. Let's go find out. So this is our lunar landscape.
Oh, cool.
So this is where we practice really with the real vision navigation systems, practicing our landing on the moon, terrain recognition and all that. Got some weeds out there, which we don't expect to encounter on the moon. But
do you do that with a drone then or something?
yeah, we do with a big drone, but it has the actual cameras and the actual software that the lander has on it, so we can practice testing that software. And,
Yeah.
which I'll tell you is pretty wild when you're like out there standing in that and you're in the middle of a cow field in Texas, like thinking we're like really figuring out how to land on the moon in the middle of the field.
Definitely.
It's
Definitely.
pretty cool.
That's awesome.
Let me see, so one of these guys ready. Hey guys, when should we head out?
I think we'll be good for 2:30.
2:30.
Down there.
Okay.
Yeah.
Like it?
We'll shoot for a hot fire at
2:30. Okay, so we have 14 minutes. Okay.
If it's okay, I was hoping to set up a high speed too from some kind of vantage point.
Okay, well we got like 15 minutes, so we better go.
Yeah. Cool.
It's like looking at welding, kind of like just look over at those poles instead of like straight at it, because after it's done, it will leave a little hysteresis in your eyes. It's not gonna hurt you, but
Right.
it's
Just a little bright.
Yeah, a little bit. Okay.
Cool.
So the vent and the press. Also, just the act of venting the tank actually cools the liquid oxygen too. It causes it to, in the tank, it causes it to boil. And as it boils, it removes heat from the rest of the bulk liquid.
Yep. Thermodynamics doing their thing.
Yeah.
Right.
Yeah, it's called saturation. So it's the same thing we do on the launch pad. We just put the liquid oxygen in. It doesn't really matter what temperature it is. And then we just sit there, and you'll notice the boiling rate goes down, 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 down as it self-cools.
Okay.
Yeah. Yeah, the other thing you can do is bubble little helium into the liquid oxygen, let it percolate up through the oxygen. And as it does that, there's a concentration gradient. Nature abhors a gradient of any type, not just vacuums. So you got pure helium, oxygen, and the oxygen tries to infiltrate that pure helium, so it evaporates into that. And in the process, it releases heat and cools the oxygen, and the helium convects it up and boils it out the top. So that's another way we cool it. It's called, sometimes you'll hear helium bubbler on or something, and really anybody that's launching rockets, and that's what it is. You bubble helium from the bottom and out the top, and it cools it.
Huh.
Kind of a weird way to cool, but
Yeah.
There we go.
There we go.
Hello!
Holy crap!
You okay?
That was awesome!
Yeah, you get 4 of those together, it gets really interesting.
Holy crap! That was so much brighter than I thought, and louder too. That was
Got a little
awesome.
dust coming back toward us too.
Holy crap! Look at that. Okay, that was amazing.
Cool to go to work and be scared by the things you work on. All right, I got to go back to working on the rims.
Awesome. Hey, thank you so much for your time. It was
Bye-bye.
really awesome. Thank you. Thank you so much, the teams here at Firefly Aerospace, for letting me walk around and just check out all this stuff. I love it. And I got to tell you, that was the closest I've ever been to a rocket engine firing. It's a lot brighter than I thought, and it's pretty stinking loud. That was amazing. So thank you for that. I owe a huge thank you to my Patreon supporters for helping make videos like this and everything else we do here at Everyday Astronaut possible. If you want to help support what I do and gain access to our awesome Discord community or lots of other behind the scene things, head on over to patreon.com/everydayastronaut. And while you're online, be sure and check out our awesome web store like this, the Aerospike shirt, which is fitting considering Firefly was originally trying to do that Aerospike engine, or lots of other fun stuff like the rest of our schematics collection, our Future Martian shirt, Full Flow, lots of fun stuff at everydayastronaut.com/shop. Thanks everybody, that's gonna do it for me. I'm Tim Dodd, the Everyday Astronaut, bringing space down to Earth for everyday people.